By considering a MIMO system as shown in figure 2 from a point-to-point MIMO link under frequency non-selective feeding with NT transmit antennas and NR receive antenna, we show this input-output relation expressed in equation 1, that is y of n equal to h of xn plus u of n, where x of n is the NT1 transmitted signal vector at any instant n, y of n having order of nr:1 received signal vector time instance, and h having order of nt by nr channel matrix subject to block fading, and un is having the order of nr by 1 received noise vector. So we know the transmitted matrix having order of mt by 1 as a column matrix, and s of I is the ith component transmitted from antenna I. So we consider the channel to be a Gaussian channel such that the elements of S are considered to be independent, identically distributed Gaussian variables. And we know if the channel is unknown at the transmitter, by assuming that the signal transmitted from each antenna have equal power of E of S by MT, the covariance matrix can be found out by showing the equation 2. Then, where E of S is the power across the transmitter irrespective of the number of antenna M of R, and I M of T is the identity matrix. So we are able to find the total amount of signal to noise ratio that can be written in equation 3. We have shown in figure 3 by considering 2x2 MIMO system, where the received signal vector on the first receive antenna is shown in the figure 4, equation 4, and the second receive signal on the second receive antenna has been shown in equation 5. So by finding out the different components, we can express the received vector in the form of R equal to Hs plus N as shown in equation 7. Now we are able to find out the channel H matrix as shown in the equation 8 because we are using the Rayleigh and Rician flat feeding channels. So we will say by considering the real world MIMO channel, the behavior of H can significantly deviate from H of W due to a combination of inadequate antenna spacing or inadequate scattering that leading to spatial fading correlation function. So we can say the presence of a fixed line of sight component in the channel will result in the Rician fading, and in the presence of line of sight component between the transmitter and receiver, and the MIMO channel may be modeled as sum of two components. One is the fixed component and another is the fading component, where first one is the line of sight component. We are able to obtain its value by putting k is greater than equal to 0, and when we put value of k equal to infinity, it corresponds to a non-fading channel. So in general we will say the real world MIMO channels, it will exhibit some combination of both Rician fading and spatial fading correlation. Now so we can deduce that with appropriate knowledge of MIMO channel at the transmitter, the signaling strategy can be appropriately adapted to meet the performance requirements. That means the channel state information could be complete. That is, knowledge of the channel is must when we want to provide or when we want to achieve the concept of equalization that mitigate the inter-symbol interference. As we know, the equalization, because equalization is a technique, a signal processing task that is used for the mitigation of inter-symbol interference. As we have already discussed, we will say for an equalizer to mitigate the inter-symbol interference introduced by the channel, it must have an estimate of the channel impulse or frequency response. Because the wireless channels varies over time, the equalizer must learn the frequency response or the channel frequency response of the channel that is known as training, and then it must have to update the estimate of the frequency response that is known as tracking. So we say the process of equalizer training and tracking is often referred to as adaptive equalization. Since the equalizer adapts to changing channel, so we will say in general the training is done by sending a fixed length known bit sequence over the channel. The equalizer at the receiver uses the known training sequence to adapt its filter coefficient to match the channel frequency response. Specifically, the equalizer filter coefficients are updated to minimize the error between the actual channel output and the output resulting from the non-training sequence. So this is the concept of equalization. So we will say the training process assume that the channel is relatively constant over the length of the training sequence. Otherwise it is difficult or it is impossible to provide the equalization. Or we can say the channel, if the channel can't be estimated properly. After training, the equalizer coefficients are matched to the channel and the data can be transmitted. So during the transmission of user data, an adaptive algorithm is used on the received data to continually update the equalizer coefficients. Then these type of techniques are broadly classified into two different tasks. One is the linear and another is non-linear. In case of linear, we know that we are having a zero forcing and minimum mean square error. These two type of equalizer are there, and no doubt the zero forcing eliminates all the inter-symbol interference, but it produces a noise enhancement. So we prefer second one equalizer, that is minimum mean square errors as compared to the zero forcing. The minimum mean square error equalizer minimizes the expected mean square between the transmitted symbol and the symbol detected at the equalizer output. So thereby providing a better balance between inter-symbol interference mitigation and noise enhancement. Because of the more favorable balance in case of minimum mean square error, we have better bit error rate performance than the system that uses zero forcing equalizer. And among the non-linear type of equalizers or equalization techniques, we are having the decision feedback equalization. That is the most common, since it is fairly simple to implement and doesn't suffer from any kind of noise enhancement. So we have shown the different samples in the equation 11 by applying concept of equalization, and we obtain the discrete time equivalent to the analog equalizer as shown in equation 13, and the power spectrum has been shown in the equation 14. So we will say from this equation 14, it is clear that if the channel h of z is sharply attenuated at any frequency within the bandwidth of interest, as is common on frequency selective fading channels, the noise power will be significantly increased. So this motivates an equalizer design that better optimizes between inter-symbol interference and mitigation and the type of noise enhancement. And one such type of equalizer is the MMSE equalizer. In equation 15, we have considered the zero forcing equalizer, which show why h of inverse is given by sum of two components x and n of h minus 1. To solve the value for x, we know that we have to find out the matrix W of ZF, which satisfy h equal to 1. The zero forcing linear detector for meeting this constant is shown in equation 16, and we are able to find the covariance matrix of the affected noise in equation 17. So it has been clear from this equation that the noise power may increase because of the factor. If the number of transmitter and the receiver antenna is not same, we may multiply by more Penrose generalized inverse pseudo inverse to achieve a similar zero forcing result. And in case of minimum mean square, we have shown the output of minimum mean square by considering MMSE detector operation x of k given by SGN W of MMSE with the y component. That means we have shown to solve for value of x, we are in need of equation 19 and 20. And the signal to noise ratio in case of minimum mean square error has been shown in equation 21. Or we can say at a high signal to noise ratio, this minimum mean square error becomes equivalent to zero forcing. Then we are having the successive interference cancellation. When the signals are detected successfully, the output of the previous detectors can be used to aid the operation of the next ones, which leads to a decision directed detection algorithm, which includes successive interference cancellation, parallel interference cancellation, and the multi-stage detection. So we can use these type of successive interference cancellation technique along with the equalizer, which provides or which enables a different type of equalizer by considering the combination of zero forcing along with the successive interference cancellation, minimum mean square along with successive interference cancellation, that shown the better performance and better results as compared to the zero forcing and minimum mean square error. We know for the MMSE detector, the significance of successive interference cancellation is not only to minimize the amplification of the noise, but also the cancellation of the interference from other antennas. In addition to this, we are having an opportunity to improve the performance by optimal ordering, that is by providing successive interference cancellation tasks along with the ordinary ZF and MMSE equalizers. And in case of maximum likelihood, that is another type of equalizer, we know the ML detection always determines the estimate transmitted signal vector as we have shown in equation 24, and the performance or the ML receiver performs optimum vector decoding, that is optimal in the sense of minimizing the error probability. So ML receiver, we can say ML receiver is a method that compare the received signal with all the transmitted signal vectors, which is again modified by channel matrix H, and it estimates the transmit symbol vector C. According to the maximum likelihood principle, which we have shown in equation 25, we can say we are able to obtain the output in the case of maximum likelihood that works on the concept of consideration of maximum probability. That is why it is known as maximum likelihood. And the last type of equalizer is the sphere decoder. The main idea behind the sphere decoder is to limit the number of possible code words by considering only those code words that are within the sphere and are centered at the received signal vector. So we will say sphere decoding method intends to find the transmitted signal vector with the minimum ML metric. So by providing or by using this sphere decoder, we are also able to improve or to mitigate the inter-symbol interference that we have shown in the different equation. Now we want to explain the concept of how we have analyzed the different type of equalizer, how we have compared just by providing the concept of simulation. So we have done the simulation by using MATLAB. Then by using MATLAB, we have obtained the different graphs. Different figure shows, first two figures shows the concept of or the waveforms of the ZF equalizer in both the Rayleigh and the Rician fading channel. In presentation, we have shown these two figures as figure 4. One is for Rayleigh channel, other is for Rician channel. And the concept of MMSE is shown in figure 4, ZF is in figure 5. Then by combining ZF SIC in figure 6 in both the channels, figure 7 shows MMSE with SIC. Then we show figure 8. Figure 8 shows the different type of equalizers for ML equalizer that show the comparison of bit error rate for both modulations. Then in the last diagram in figure 9, which shows the comparison of bit error rate for BPSK with different type of equalizers that we are using, that is zero forcing, minimum mean square error, zero forcing with successive interference cancellation, minimum mean square error with successive interference cancellation, maximum likelihood, and the sphere decoder. And now we come to the last conclusion. So we have considered, by considering the different simulation results and by obtaining the number of observations, it has been concluded that the sphere decoder provides the best performance as compared to all the equalizer. No doubt the maximum likelihood also perform better as compared to the other, but having one of the drawback. What is that drawback? The complexity of this maximum likelihood decoder goes on increasing as we move to higher modulation techniques, whereas the complexity in case of sphere decoder, that depends upon the initial radius that is to be chosen. So we will say the sphere decoder provides the best performance as compared to all the equalizers. Thanks.